Galaxies are moving away, the quiet expansion of the universe. Most of the galaxies in the universe are moving away from us. Not a few of them, not some unusual subset, nearly all of them. The farther away a galaxy is, the faster it recedes. This has been measured and confirmed over the course of nearly a century, using different instruments, different methods, and different teams of scientists working independently. The pattern holds in every direction. It holds whether you look toward the constellation Virgo or toward the southern sky. It is one of the most consistent observations in all of modern science. The universe, it turns out, is getting larger. Not in the way a balloon gets larger when you add air. Not in the way a city expands outward as new houses are built at its edges. The expansion of the universe is something different from any ordinary kind of growing. It does not have an edge that pushes outward. It does not have a center from which things move away. The space between galaxies is itself stretching everywhere, all at once, and it has been doing this for billions of years. To understand what this means and how we came to know it, it helps to start with what a galaxy actually is and how far apart they sit from one another. A galaxy is a collection of stars held together by gravity. Some galaxies contain a few billion stars, others contain hundreds of billions. The Milky Way, the galaxy we live in, holds somewhere between 100 billion and 400 billion stars, depending on which estimate you trust. The Sun is one of them. It sits in a spiral arm, roughly 2/3 of the way out from the center, orbiting the galactic core at a speed of about 220 kilometers per second. It takes the Sun roughly 230 million years to complete a single orbit around the Milky Way. That orbital period is sometimes called a galactic year. The Milky Way is not alone. It belongs to a small collection of galaxies called the Local Group. The Local Group contains about 80 known galaxies, most of them small and faint. The two largest members are the Milky Way and the Andromeda Galaxy, which sits roughly 2.5 million light-years away. A light-year is the distance light covers in 1 year, which works out to about 9.46 trillion kilometers. So the Andromeda Galaxy is approximately 24 trillion kilometers from here, give or take. These are distances that don't translate well into everyday experience. They are simply large. Beyond the Local Group, galaxies continue outward in every direction. They cluster into larger structures. Groups of galaxies form clusters, clusters form superclusters, and superclusters are connected by long, thin filaments of matter, creating a pattern that cosmologists call the cosmic web. Between the filaments are enormous regions of nearly empty space, called voids. The whole thing, taken together, looks less like a scattering of points and more like a vast, loosely connected net. The observable universe, the portion of the universe from which light has had time to reach us since the beginning, spans about 93 billion light-years across. That number is larger than 13.8 billion light-years, even though the universe is about 13.8 billion years old, because space has been expanding during the time that light has been traveling. Objects that emitted their light billions of years ago are now much farther away than they were when that light left them. Within this observable volume, there are an estimated 2 trillion galaxies. That number comes from deep survey data collected by the Hubble Space Telescope and other instruments. 2 trillion is a rough count, and it includes many galaxies too small and too faint to see individually. But even as a rough figure, it gives a sense of scale. The universe is not empty. It is full of structure, organized on every level from individual solar systems up through galaxies, clusters, and filaments, stretching across hundreds of millions of light-years. The fact that these galaxies exist is one thing. The fact that nearly all of them are moving away from us is something else entirely. The story of how this was discovered begins in the early 1900s, when astronomers were still debating whether the Milky Way was the entire universe or just one part of something much larger. At that time, the fuzzy patches of light visible through telescopes were called nebulae, a Latin word meaning clouds. Some astronomers believed they were clouds of gas inside our own galaxy. Others suspected they were separate galaxies far beyond the Milky Way, each containing billions of their own stars. In 1912, an astronomer named Vesto Slipher began measuring the light from these nebulae more carefully. He used a technique called spectroscopy, which involves splitting the light from an object into its component wavelengths, the same way a prism splits white light into a rainbow. Every element, when heated, produces light at very specific wavelengths. Hydrogen produces light at certain wavelengths, helium at others. Calcium, sodium, oxygen, each has its own pattern, like a fingerprint. Slipher noticed something consistent. When he looked at the spectral fingerprints from distant nebulae, the patterns were there, but they were shifted. The lines appeared at slightly longer wavelengths than expected. In visible light, longer wavelengths correspond to the color red, so this shift became known as a redshift. A redshift in the light from an object means that the object is moving away from the observer. The greater the shift, the faster the object is receding. Slipher found that nearly all the nebulae he measured were redshifted. Nearly all of them were moving away. This was an unusual finding, but at the time, it didn't lead to any grand conclusion. The distances to these objects were not well known, and it wasn't yet established that they were even separate galaxies. That part came later. In 1924, Edwin Hubble, working at the Mount Wilson Observatory in the mountains above Los Angeles, used a powerful telescope to resolve individual stars within the Andromeda Nebula. One of the stars he identified was a type of variable star called a Cepheid. Cepheid stars pulse in brightness at a rate that is directly related to how bright they actually are. By measuring how quickly a Cepheid pulses, you can determine its true luminosity. And by comparing its true luminosity with how bright it appears from Earth, you can figure out how far away it is. Hubble's measurement showed that the Andromeda Nebula was far outside the Milky Way. It was a separate galaxy, at least several 100,000 light-years away, later refined to about 2.5 million light-years. This settled the debate. The Milky Way was not the whole universe. It was one galaxy among many. A few years later, Hubble combined his distance measurements with redshift data, much of it originally collected by Slipher. He plotted the speed at which galaxies were receding against their distance. The result was a straight line. The relationship was proportional. A galaxy twice as far away was moving away twice as fast. A galaxy 3 times as far away was receding 3 times as fast. This relationship is now known as the Hubble-Lemaître law, named after Hubble and the Belgian astronomer Georges Lemaître. Lemaître had actually derived the same relationship from Einstein's equations of general relativity in 1927, 2 years before Hubble published his observational results. Lemaître approached the problem from the theoretical side, working out mathematically what an expanding universe would look like. Hubble approached it from the observational side, measuring galaxies one by one. They arrived at the same conclusion from different directions. The number that describes this relationship is called the Hubble constant. Its current best estimates place it somewhere around 67 to 73 kilometers per second per megaparsec. A megaparsec is about 3.26 million light-years. What the Hubble constant tells you is how fast a galaxy is receding based on how far away it is. A galaxy sitting 1 megaparsec away is moving away at about 70 kilometers per second. A galaxy 10 megaparsecs away is moving away at about 700 kilometers per second, and so on. There is still some disagreement among scientists about the exact value of the Hubble constant. Different measurement techniques produce slightly different results, and this discrepancy has its own name, the Hubble tension, but the disagreement is over the precise rate of expansion, not over whether the expansion itself is real. That part is firmly established. The natural question that follows from all of this is what exactly is expanding? And the answer is not quite what most people expect. It would be natural to picture galaxies as objects flying outward through space, like fragments from an explosion moving through a room. But that picture is not accurate. The galaxies are not moving through space in the usual sense. Space itself is expanding. The distance between galaxies is increasing not because the galaxies are traveling through some fixed background, but because the background itself is stretching. There is a simple way to think about this. Imagine a long rubber band with dots drawn on it at regular intervals. Each dot represents a galaxy. Now stretch the rubber band. As it stretches, every dot moves away from every other dot. Dots that were close together move apart slowly. Dots that were far apart move apart quickly. No dot is at the center. No dot is the origin of the stretching. The stretching is happening everywhere along the band, and every dot sees the same pattern, all other dots receding, with the more distant ones receding faster. Another version of this uses the image of raisin bread dough rising in an oven. The raisins are galaxies. As the dough expands, every raisin moves away from every other raisin. From the perspective of any single raisin, it looks like all the others are rushing away, and the ones that started farther away are moving faster. But no raisin is doing anything. The dough between them is what's growing. These analogies have limits. The rubber band is one-dimensional. The bread dough has edges. The universe, as far as we can tell, does not have edges, and it is not expanding into anything outside itself. Space is all there is, and it is the space itself that is growing. There is no region outside the universe that the expansion is filling. The expansion is a property of the geometry of space on the largest scales. One thing the expansion does not do is pull apart objects that are held together by stronger forces. Gravity, for instance, is far stronger than the expansion effect at the scale of a galaxy or a solar system. The Milky Way is not getting larger. The Earth is not drifting away from the Sun. Atoms are not being stretched apart. The expansion only becomes noticeable across distances of millions of light years between structures that are not gravitationally bound to one another. Within a galaxy, within a cluster, within a solar system, things behave normally. The expansion is a large-scale phenomenon. It operates in the spaces between the largest structures, not inside them. This is part of why the expansion went unnoticed for so long. Nothing in the immediate vicinity of Earth changes because of it. The planets orbit the Sun as they always have. The stars in the Milky Way maintain their positions relative to one another, guided by the galaxy's gravitational field. It is only when you look at objects millions or billions of light years away that the expansion shows itself, in the quiet reddening of their light and the ever-growing distances between them. There is an important detail embedded in the fact that there is no center to the expansion. If you were standing in a different galaxy, anywhere in the observable universe, you would see the same thing, all distant galaxies receding, all of them following the same proportional pattern, more distant ones moving faster. This is not because the Earth or the Milky Way occupies a special position. It is because the expansion is uniform. Every point in space sees the same picture. The pattern is built into the geometry of the expansion itself. This can be difficult to picture. It seems like there should be a center, some point from which everything is moving away. But there is. The expansion is not an explosion that happened at a single location. It is a stretching of all of space, everywhere, simultaneously. The Big Bang, despite its name, was not a detonation in some pre-existing void. It was the beginning of space and time themselves. Every point in the universe was once the same point. As space expanded, every point moved away from every other point. No location is more central than any other. The evidence for the expansion doesn't rest on a single type of observation. There are several independent lines of evidence, gathered using different methods, that all point to the same conclusion. The most direct is the redshift of galaxies. The spectral lines of distant galaxies are shifted toward longer wavelengths, and the amount of shift correlates with distance, just as the Hubble-Lemaître law predicts. This has been confirmed for tens of thousands of galaxies across wide regions of the sky. A second, independent line of evidence comes from something called the cosmic microwave background radiation. In 1965, two physicists named Arno Penzias and Robert Wilson were working at Bell Telephone Laboratories in New Jersey. They were testing a large, horn-shaped antenna that had been designed for satellite communication. When they pointed it at the sky, they detected a faint but persistent signal, a low hum of microwave radiation coming from every direction, with no identifiable source. It was the same in every part of the sky, day or night, in every season. They couldn't figure out what was causing it. They even checked whether pigeons nesting in the antenna might be responsible. They cleaned the antenna and tested it again. The signal remained. Around the same time, a group of physicists at Princeton University, just 30 miles away, had been working on a theoretical prediction. If the universe had once been extremely hot and dense, as the Big Bang model suggested, then the radiation from that early period should still be present, stretched by the expansion of space into the microwave part of the electromagnetic spectrum. It would appear as a faint glow coming from all directions, with a temperature just a few degrees above absolute zero. When the Princeton team heard about Pensier's and Wilson's signal, they recognized it immediately. It was the remnant heat of the early universe. It was the afterglow of the Big Bang, cooled and stretched over 13.8 billion years of expansion, now sitting at a temperature of about 2.725 Kelvin, roughly 270 degrees below 0 Celsius. Penzias and Wilson received the Nobel Prize in Physics in 1978 for the discovery. The cosmic microwave background, as it came to be called, has been studied extensively since then. It has been mapped in detail by a series of space missions, COBE in the early 1990s, WMAP in the 2000s, and the Planck satellite in the 2010s. Each mission produced a sharper picture. The maps show that the radiation is almost perfectly uniform across the entire sky, with tiny fluctuations, temperature differences of about 1 part in 100,000. Those tiny fluctuations correspond to slight differences in the density of matter in the early universe, and they are the seeds from which galaxies and galaxy clusters eventually formed. The cosmic microwave background tells us something else, too. It tells us the composition of the universe. By analyzing the pattern of fluctuations in the microwave background, scientists have been able to calculate what the universe is made of in broad terms. The answer is unexpected. Ordinary matter, the stuff that makes up stars, planets, gas, dust, water, people, everything visible, accounts for only about 5% of the total energy content of the universe. 5%. Everything we can see and touch and measure directly, all the atoms in the periodic table, all the light from all the stars, is a small fraction of what exists. About 27% of the universe is dark matter. Dark matter does not emit light. It does not absorb light. It does not reflect light. It is invisible to every telescope that has ever been built. But it has mass, and mass produces gravity, and its gravitational effects are visible everywhere. Galaxies rotate faster than they should based on the amount of visible matter they contain. Galaxy clusters hold together more tightly than their visible mass would allow. The pattern of fluctuations in the cosmic microwave background matches theoretical predictions only when dark matter is included in the calculations. Something is there. It interacts with gravity. It does not interact with light. Nobody knows what it is made of. It has never been directly detected in a laboratory, despite decades of searching. The remaining 68%, the majority of the universe, is something called dark energy. Dark energy is even more mysterious than dark matter. It is not a substance in the usual sense. It is a property of space itself, an energy that fills the vacuum and exerts a kind of pressure that pushes space apart. Dark energy is what is causing the expansion of the universe to accelerate. That last part, the acceleration, is a relatively recent discovery, and it changed the way scientists think about the future of the universe. For most of the 20th century, the assumption was that the expansion of the universe had been slowing down since the Big Bang. This made intuitive sense. Gravity pulls matter together. Every galaxy exerts a gravitational pull on every other galaxy. Over time, this pull should act as a brake on the expansion, gradually slowing it the way friction slows a ball rolling across a floor. The open question was whether the expansion would slow to a stop and reverse, leading to a collapse, or simply slow down forever, approaching zero but never quite reaching it. In the late 1990s, two teams of astronomers set out to measure exactly how much the expansion was decelerating. They did this by studying a particular type of exploding star called a Type Ia supernova. These explosions happen in binary star systems, where a dense remnant called a white dwarf orbits alongside a normal star. The white dwarf pulls matter from its companion, gaining mass over time. When it reaches a specific critical mass, about 1.4 times the mass of the Sun, it can no longer support itself, and it detonates in a thermonuclear explosion. The useful thing about Type Ia supernovae is that because they all explode at roughly the same mass, they all produce roughly the same amount of light at their peak. This makes them reliable distance markers. If you know how bright something actually is, and you can see how bright it appears from Earth, you can calculate how far away it is. Astronomers call objects like this standard candles. The two teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, observed dozens of distant type Ia supernovae and measured both their brightness and their redshift. The expectation was that the distant supernovae would appear slightly brighter than the simple expansion model predicted, indicating that the expansion had been slowing over time. Instead, they found the opposite. The distant supernovae were dimmer than expected. They were farther away than they should have been. The expansion had not been slowing down, it had been speeding up. Both teams published their results in 1998. The findings were unexpected. Gravity should have been slowing the expansion, not letting it accelerate. Something was actively pushing the universe apart, working against gravity on the largest scales. That something was given the name dark energy. The discovery earned the Nobel Prize in Physics in 2011. Saul Perlmutter, Brian Schmidt, and Adam Rees were recognized for their work, leading the two teams that independently reached the same conclusion. Science magazine had already named the discovery the breakthrough of the year in 1998. Dark energy makes up about 68% of the total energy content of the universe. Its nature is not known. The leading candidate is something called the cosmological constant, a term Einstein originally added to his equations of general relativity in 1917 to allow for a static, non-expanding universe. When Hubble's observations showed that the universe was expanding, Einstein reportedly called the cosmological constant his greatest mistake and removed it from his equations. Decades later, the discovery of accelerating expansion brought it back. The cosmological constant, if that is what dark energy is, represents a fixed energy density built into the fabric of space itself. It does not dilute as the universe expands. As matter thins out and spreads across a growing volume, the energy density of dark energy stays the same. This means that as the universe gets bigger, dark energy becomes a larger and larger share of the total. Its influence grows, not because it is getting stronger, but because everything else is getting weaker. For the first several billion years after the Big Bang, the universe was dense enough that the gravitational pull of matter dominated. The expansion was slowing, but as space expanded and matter spread out, there came a point, roughly 5 billion years ago, when the universe was about 9 billion years old, when the density of matter dropped below the density of dark energy. After that crossing point, dark energy took over. The expansion began to accelerate, and it has been accelerating ever since. The implications of this are worth sitting with. If the expansion continues to accelerate, and under the standard cosmological model, the distances between galaxy clusters will grow faster and faster. Galaxies that are currently visible to us, even with the most powerful telescopes, will eventually recede so quickly that their light can no longer reach us. Their photons will be stretched to infinite wavelengths, and from our perspective, they will fade from view. This will happen slowly, over tens of billions of years, but the direction is clear. The observable universe, in terms of the number of galaxies we can detect, will shrink over time. More and more of the cosmos will slip beyond our horizon. Not everything will be lost. Gravity still holds local structures together. The Milky Way, the Andromeda Galaxy, and the rest of the local group are bound to each other by mutual gravitational attraction. The expansion of space is not strong enough to overcome that bond. These nearby galaxies will remain together. In fact, the Milky Way and Andromeda are currently approaching each other at about 110 kilometers per second and are expected to merge in roughly 4 to 5 billion years. The result will be a single, larger elliptical galaxy, a quiet merger unfolding over hundreds of millions of years, reshaping the structure of stars without destroying them. But beyond the local group, the picture changes. Galaxy clusters that are not gravitationally bound to ours will recede. Superclusters will drift apart. The cosmic web, with its filaments and voids, will stretch thinner. In the very distant future, an observer in what was once the Milky Way would look outward and see only the stars of the merged local galaxy. The rest of the universe would be dark and empty, not because nothing is there, but because the light from those distant structures can no longer make the trip. This scenario is sometimes called the heat death of the universe. It is not a dramatic ending. It is a slow dimming. Over trillions of years, stars burn through their fuel and stop shining. New stars form at a declining rate as the available gas runs out. The last red dwarf stars, small, cool, and efficient, might burn for trillions of years, but eventually they too will exhaust their hydrogen. What remains is a universe of fading remnants. White dwarfs cooling toward darkness, neutron stars spinning down, black holes slowly evaporating over timescales that dwarf the current age of the universe. This is the most widely accepted projection under the current standard model of cosmology, which is called the lambda-CDM model. Lambda refers to the cosmological constant, and CDM stands for cold dark matter. The model fits the available data well: the redshifts, the cosmic microwave background, the large-scale distribution of galaxies. It is not the final word. Science does not deal in final words, but it is the best framework we currently have. There are open questions. The nature of dark energy is one of the largest. If dark energy is indeed the cosmological constant, a fixed property of space, the future unfolds as described above. But there are other possibilities. Dark energy might change over time. It might weaken, allowing gravity to eventually halt and reverse the expansion. It might strengthen, accelerating the expansion so much that eventually even galaxies, then stars, then atoms are torn apart in what has been called a big rip. Recent data from the Dark Energy Spectroscopic Instrument, published in 2025, has hinted that dark energy may not be perfectly constant, that its density might be slowly changing. This is not confirmed. The uncertainties are large, but it is a live area of research. Dark matter, too, remains unexplained at a fundamental level. Its gravitational effects are well documented and woven into the standard model, but no particle of dark matter has ever been directly detected. Experiments deep underground, shielded from cosmic rays, have been searching for dark matter particles for decades. So far, nothing has been found. This does not mean dark matter doesn't exist. The gravitational evidence is strong, but what it is exactly remains unknown. The Hubble constant itself is still a matter of active debate. Measurements using the cosmic microwave background, as analyzed by the Planck satellite, give a value of about 67.4 kilometers per second per megaparsec. Measurements using Cepheid variable stars and type Ia supernovae, closer to home, give a value closer to 73. The gap is small in absolute terms, but large enough to be statistically significant. Either one of the measurement methods contains an undetected error, or there is something about the expansion of the universe that the current model does not fully capture. The Hubble tension, as it is called, is one of the most discussed puzzles in modern cosmology. Whether the universe is finite or infinite is another open question. We can only see the observable portion, the sphere from which light has had time to reach us. Beyond that horizon, there may be more of the same, more galaxies, more clusters, more of the cosmic web stretching outward without end. Or the universe might curve back on itself in a way that makes it finite, but without boundaries, like the surface of a sphere that has no edge, but does have a definite area. Current measurements show that the geometry of the universe is very close to flat, which is consistent with either possibility. What preceded or caused the Big Bang is also not known. The Big Bang model describes the evolution of the universe from a very early, very hot, very dense state. It does not describe the moment of origin itself. The physics that governs the first fraction of a second, the period before the known forces of nature had separated and settled into their current forms, is still being worked out. There are theoretical frameworks, like cosmic inflation, that describe a brief period of rapid expansion in the universe's earliest moments, but these are still being tested and refined. So the picture, taken as a whole, is one of large-scale motion happening quietly and steadily. Galaxies move apart, space stretches, the expansion accelerates, and all of this happens without any visible cause, without any sound, without any disruption to the ordinary workings of the local universe. The sun still burns, the Earth still orbits, stars form and die in the usual ways. The expansion of the universe is the largest scale process occurring in nature, and it is also one of the most invisible. Its effects are only apparent when you look across millions of light years, across distances so large that everyday experience offers no useful comparison. The light arriving from a galaxy a billion light-years away left that galaxy a billion years ago. During the time it traveled, the space it was crossing expanded. The galaxy that emitted the light is now farther away than it was when the light began its trip. The light itself has been stretched by the expansion, shifted toward longer wavelengths. By the time it reaches a telescope on Earth, it carries information about two things: the state of the galaxy when the light was emitted and the amount of expansion that occurred while the light was in transit. Every distant observation is also an observation of the past, and every measurement of redshift is also a measurement of how much space has grown. There is something quiet about this. The universe is full of violent events: supernovae, collisions between galaxies, jets of matter ejected from black holes at nearly the speed of light. But the expansion itself is not violent. It is steady. It is gradual. It is happening right now in the spaces between galaxy clusters, in regions so vast and so empty that nothing is there to notice it. No star has ever been pulled apart by the expansion. No planet has been affected. The expansion works on a scale so large that everything we know and see fits comfortably within the structures that gravity holds together. The Andromeda galaxy is moving toward us. It has been doing so for billions of years. The gravitational pull between the Milky Way and Andromeda is stronger than the expansion of space at the distance that separates them. So while the rest of the universe drifts apart, these two galaxies are falling toward each other, closing the gap at roughly 110 kilometers per second. In about 4 to 5 billion years, they will begin to merge. The merger will take hundreds of millions of years. Stars from one galaxy will pass through the other, rearranging into new orbits. The shapes of both galaxies will change, stretching and twisting before settling into a single, larger structure. Very few stars will actually collide. Galaxies are mostly empty space, and stars are very far apart relative to their size. The merger will be a rearrangement, not a crash. This is a local event, playing out within the gravitational neighborhood. Beyond that neighborhood, the expansion continues. The Virgo cluster, a large collection of galaxies about 54 million light-years away, is receding from us. The Coma cluster, about 320 million light-years away, is receding faster. And galaxies at the edges of the observable universe, those whose light has been traveling for more than 13 billion years, are receding at speeds that, when calculated properly, exceed the speed of light. This sounds like a contradiction of the rules of physics, but it is not. The speed limit imposed by special relativity, the idea that nothing can travel faster than light, applies to objects moving through space. It does not apply to the expansion of space itself. Two galaxies can be moving apart faster than light, not because either one is traveling through space at superluminal speed, but because the space between them is expanding at a rate that adds up over a great enough distance to more than 300,000 kilometers per second. Neither galaxy is doing anything unusual. The space in between is simply growing that fast. This means that there are galaxies in the observable universe whose light we can see, but which are currently moving away from us faster than the speed of light. The light we see from them was emitted long ago, when the distance between us was smaller and the recession speed was lower. That light has been in transit for billions of years, and during that time, the galaxy has continued to recede. It is now beyond the point where any new light it emits could ever reach us. We can see its past, but not its present or its future. The number of galaxies in this situation is growing. As the expansion accelerates, more and more galaxies cross the threshold where their recession speed exceeds the speed of light. Their light redshifts further and further, growing dimmer and longer in wavelength until it becomes undetectable. They don't vanish in any sudden way. They fade. This fading is one of the consequences of accelerating expansion. The observable universe, the sphere of galaxies from which light can still reach us, will contain fewer and fewer objects over time. The cosmic microwave background itself will eventually redshift to wavelengths so long that no instrument could detect it. The evidence for the Big Bang, for the expansion, for the existence of other galaxies beyond the local group, all of it will eventually be erased from the sky, not by destruction, but by distance. An astronomer living trillions of years from now, in the merged remnant of the Milky Way and Andromeda, might look outward and see only their own galaxy's stars against an otherwise dark sky. Without evidence of other galaxies, without the cosmic microwave background, without detectable redshift, they would have no way of knowing that the universe is expanding, no way of knowing it was ever different. The information would still exist, in principle, encoded in photons stretched beyond any practical means of detection, but it would be inaccessible. The current moment in the history of the universe happens to be one where the evidence is still visible. The galaxies are still bright enough and close enough for their redshifts to be measured. The cosmic microwave background is still warm enough to detect. The fluctuations in the microwave background are still sharp enough to map. The standard candles, the type Ia supernovae, still occur within reach of our instruments. This is not a permanent condition. The window of observability is open now, and it will narrow in the future. That is not a crisis. It is a description of how things are. The universe is not arranged for the convenience of observers. It operates on its own terms, at its own scales, over its own timescales. The fact that we happen to exist during a period when the evidence is accessible is a feature of our era, not a guarantee that it will always be so. The expansion continues. It is happening now between the clusters in the spaces where nothing much exists. The Virgo cluster is a little farther away than it was a moment ago. The light from the most distant galaxies is a little redder. The cosmic microwave background is a fraction of a degree cooler than it was when the universe was half its current age. These changes are not noticeable on any human timescale. They accumulate over millions and billions of years, reshaping the large-scale structure of the cosmos in ways that are steady, continuous, and quiet. The universe is 13.8 billion years old. In that time, it has expanded from a state of nearly infinite density and temperature to the cool, sparse, structured cosmos that exists now. Stars have formed, lived, and died. Elements heavier than hydrogen and helium have been forged inside those stars and scattered into space by their explosions. Planets have formed from the debris, on at least one of those planets. Conditions allowed for the development of life, and eventually, for the development of minds capable of measuring the redshift of a galaxy a billion light-years away and working backward to figure out what it means. None of this was inevitable. None of it was planned. It is the result of physical processes playing out according to the laws of nature over a very long time in a universe that has been quietly expanding since the beginning. The galaxies continue to move apart. The space between them continues to grow. The expansion carries no sound and produces no visible effect in the local sky. It is the largest and most pervasive process in the physical universe, and it is also the most silent. Somewhere right now, a photon emitted by a distant galaxy is arriving at a telescope after a journey of several billion years, slightly redder than it was when it started, carrying in its wavelength a record of how much the universe grew while it was in transit. That record, read carefully, tells us where we are, how we got here, and where things are going. The galaxies are moving away. The distances are growing. The process has no center, no edge, and as far as we know, no end. A few billion years from now, the Milky Way and Andromeda will have merged into a single galaxy. The stars within it will continue to orbit a common center. New stars will still form from the remaining gas, though at a declining rate. The night sky from a planet inside that galaxy will be filled with stars, perhaps more densely than our current sky, as the two galaxies' populations combine. But beyond that galaxy, the sky will be darker. The galaxies that are now visible will have moved farther away. Their light will be fainter and redder. Some will have crossed the horizon entirely, their photons stretched beyond detection. The cosmic web, that network of filaments and clusters, will have thinned out across an ever larger volume. Inside the merged galaxy, none of this will be apparent. The local stars will shine as they always have. Planets will orbit. Physics will operate the same way it does now. The expansion of the universe changes nothing about the physics of everyday matter. It only changes the view of what lies beyond. The cosmic microwave background, which today fills the sky with a faint glow at a temperature of 2.725 Kelvin, will continue to cool. It has already cooled by a factor of more than 1,000 since it was first released, 380,000 years after the Big Bang. At that time, it was the temperature of a hot star, around 3000 Kelvin. The expansion of space stretched its wavelengths, lowered its energy, and shifted it from visible light into microwaves. Over the coming billions of years, it will cool further, dropping toward radio wavelengths, growing fainter, becoming harder to detect. The glow is the oldest light in the universe. It has been traveling since the universe became transparent enough to let photons move freely. Every photon in the cosmic microwave background has been crossing space for 13.8 billion years, arriving from a time when there were no stars, no galaxies, no planets, just a hot, dense fog of particles and radiation, cooling and thinning as space expanded. The fluctuations in that glow, the tiny hot and cold spots, are the imprint of conditions that existed when the universe was less than 400,000 years old. Slightly denser regions attracted slightly more matter, and over millions and then billions of years, those denser regions grew into the galaxies and galaxy clusters that exist today. The large-scale structure of the cosmos, the cosmic web, is a record of those initial conditions, stretched and evolved over deep time. The universe did not arrive at its current state suddenly. It unfolded. Hydrogen and helium, the lightest elements, were produced in the first few minutes after the Big Bang. Heavier elements came later, forged inside stars. Carbon, oxygen, nitrogen, iron, the elements that make up planets and living things, were built in the cores of massive stars and released when those stars exploded. Each generation of stars enriched the surrounding gas with heavier elements, and each subsequent generation formed from slightly richer material. The Sun and the Earth formed about 4.6 billion years ago from a cloud of gas and dust that had already been through several cycles of stellar birth and death. The atoms in the Earth, in the water, in living tissue, were made inside earlier stars. This process continues. Stars are forming right now in dense regions of gas within the Milky Way and other galaxies. Each new star inherits the chemical legacy of the stars that came before it. The supply of gas is finite, and the rate of star formation has been declining for billions of years. The peak of star formation in the universe occurred roughly 10 billion years ago, when the universe was about 3 to 4 billion years old. Since that peak, the rate has dropped. Fewer new stars are being born. The universe is agging, not in a dramatic way, but in a gradual slowing of its most productive era. None of this is separate from the expansion. The expansion set the initial conditions. It determined how quickly the early universe cooled, how quickly matter could clump together, how much time there was for structures to form. If the expansion had been slightly faster, matter would have spread too thin to form galaxies. If it had been slightly slower, the universe would have collapsed back on itself before stars had time to form. The rate of expansion, set in the earliest moments, determined the shape of everything that followed. Dark energy, whatever it is, continues to push. Its density does not change as the universe grows. Matter spreads thinner, radiation cools, but dark energy remains constant, filling every cubic meter of space with the same amount of energy regardless of how large the universe becomes. This constancy is what makes it dominant over time. In the early universe, when everything was packed tightly, matter and radiation had far higher densities than dark energy. Their gravity slowed the expansion. But as space grew and matter thinned, dark energy's share of the total increased, simply by holding steady while everything else declined. About 5 billion years ago, dark energy became the dominant component. The expansion crossed from decelerating to accelerating. The universe had been coasting, slowly losing speed, and then it began to pick up speed again. Not because dark energy suddenly appeared, it had been there all along, but because everything else had finally thinned out enough for dark energy to take the lead. The universe is now in a dark energy-dominated era. The expansion is accelerating. The distances between unbound galaxy clusters are growing at an increasing rate. The process has no known mechanism to reverse it under current models. If dark energy is the cosmological constant, it will continue at this rate indefinitely. The Hubble constant, the number that describes the current rate of expansion, captures a snapshot. It tells us how fast the expansion is happening right now, but the rate has not been constant over the life of the universe. It was much higher in the first moments after the Big Bang. It dropped as the universe expanded and matter's gravity slowed things down. It reached a minimum and then began to rise again as dark energy took over. The Hubble constant is constant only in the sense that it has the same value everywhere in space at a given moment in time. It is not constant across time. The value we measure today, somewhere between 67 and 73 kilometers per second per megaparsec, is a product of the entire history of the expansion, shaped by the interplay between matter, radiation, and dark energy over 13.8 billion years. Every time a telescope measures the redshift of a distant galaxy, it is sampling one point along that history. The collection of all such measurements, plotted together, traces the expansion curve of the universe from its earliest moments to the present. That curve contains the story. It starts steep, as the initial expansion flings matter outward at tremendous speed. It flattens as gravity breaks the expansion, and then it bends upward again as dark energy accelerates it. The curve has no planned destination. It is simply the record of what happened and what is happening. Galaxies are still forming in the universe, though the rate is declining. Gas still collapses under gravity in dense regions, igniting new stars. Supernovae still scatter heavy elements into the interstellar medium. Black holes at the centers of galaxies still grow by absorbing surrounding matter. The universe is active. It is not winding down in any way that would be noticeable over human timescales or even over the timescale of civilizations. The processes that built the current universe are still underway. They are slower now than they were a few billion years ago. But they are far from over. The expansion carries everything with it. Every structure that is not gravitationally bound to another drifts a little farther away each year. The drift is tiny, a few centimeters per second between neighboring clusters, compounded over millions of years. But compounded over billions of years, it adds up. Clusters that were once neighbors become strangers. Filaments that once connected them stretch and thin. The cosmic web loosens. There is no sound associated with any of this. No vibration, no signal. The expansion is silent. It happens in the vacuum of intergalactic space, where there is almost nothing, perhaps one atom per cubic meter, sometimes less. The emptiest regions of the universe, the great voids between filaments, are among the most vacant places that exist. And even in those voids, space is expanding. The idea that the universe is mostly empty and that its dominant component is a form of energy that nobody has ever directly observed, and that the second largest component is a type of matter that nobody has ever detected in a lab, this is the current state of knowledge. It is an honest accounting. 5% of the universe is made of the kind of matter that we understand well. The rest is dark, not dark in the sense of being threatening or hidden. Dark in the sense of being invisible to the methods we currently have for seeing. The effects are visible, the causes are not. This is where cosmology stands. The expansion is real, the acceleration is real. The darkness, the dark matter, the dark energy is real in the sense that its effects are measurable and consistent. The explanations are incomplete. The measurements continue. New telescopes, new surveys, new instruments are being built and deployed. The James Webb Space Telescope looks deeper into the past than any optical telescope before it. The Dark Energy Spectroscopic Instrument maps the positions of millions of galaxies to trace the expansion rate across cosmic time. The Vera Rubin Observatory will survey the sky with a sensitivity that previous generations of telescopes could not approach. Each of these instruments adds detail. Each measurement tightens the constraints on what dark energy might be, on how the expansion has changed over time, on whether the current model is complete or whether something is missing. The answers may come slowly. They may come in the form of small corrections to existing models, or they may come as a surprise that reshapes the entire picture. Either way, the process of looking and measuring will continue for as long as there are people building telescopes and pointing them at the sky. The galaxies are moving away. They have been moving away for as long as anyone has known to look. The space between them grows, and the rate at which it grows is increasing. The process began before the Earth existed, before the Sun existed, before the Milky Way had taken its current shape. It will continue long after. The expansion does not need anything from us. It does not require observation or understanding or acknowledgement. It simply is. It is the way the universe works at the largest scale. a continuous, quiet, ongoing stretching of the space that contains everything. The light from distant galaxies continues to arrive. It is a little redder each year, shifted by the expansion it has traveled through. Each photon carries a timestamp encoded in its wavelength, recording how much the universe has grown since that photon began its trip. The timestamps span billions of years. The oldest ones come from the cosmic microwave background, carrying information from a universe that was less than 400,000 years old. The newest come from galaxies close enough that their light has traveled only a few million years. Between the oldest and the newest, the full arc of the expansion is laid out, not in a single observation, but in the accumulated evidence of many observations made over decades, refined by each new generation of instruments. The picture is clear in its broad outlines and still fuzzy in some of its details. The broad outlines say this: the universe is expanding. It has been expanding since the beginning. The expansion is accelerating, and the cause of the acceleration is not yet understood. The details will come, or they won't. The universe does not owe anyone an explanation. It simply continues on its own terms at its own pace, filling itself with space at a rate that no force within it appears able to stop. The galaxies drift apart. The distances grow. The light travels, and some of it arrives, and some of it does not, and the boundary between the visible and the invisible shifts slowly outward, like a tide that only moves in one direction. Somewhere in the universe right now, a galaxy that has never been observed by any instrument on Earth is receding at a speed that carries it across the edge of our observable horizon. Its light will never reach us. Its stars will never appear in any catalogue. It exists, it has structure, it contains billions of stars, and from our perspective, it is gone, not destroyed, just unreachable. The expansion has placed it beyond our ability to know it is there. This is happening now, and it will keep happening at an increasing rate for as long as the expansion continues. The observable universe is not a fixed thing. It is a window, and the window is narrowing. The stars inside our own galaxy continue to burn. The planets continue to orbit. The physics that governs daily life is unchanged by any of this. The expansion is the background condition, the setting, not the story. The story is told by the things that happen within the structures that gravity holds together, the formation of stars, the chemistry of planets, the slow unfolding of time in the local universe. The expansion is the frame. The frame is growing. The things inside the frame carry on as they are. And the space between the frames, the space between the galaxies, between the clusters, between the filaments, that space grows and grows and grows at a pace that picks up slightly with each passing billion years, carrying the most distant parts of the universe a little farther beyond reach with every moment that passes. The cosmic microwave background still fills every direction of the sky. Its temperature is 2.725 Kelvin. It has been cooling since the universe was young. It will keep cooling as space continues to expand. Dark energy still fills every cubic meter of space. Its density has not changed. It has no known source and no known structure. It is everywhere and it is constant. Dark matter still holds galaxies together. It shapes the rotation curves of spiral arms. It anchors clusters. It has never been seen directly. Ordinary matter, the 5%, makes up the stars and the gas and the dust. It makes up the planets. It makes up the elements that were forged inside earlier generations of stars and scattered when those stars ended. The expansion of the universe is not something that happened. It is something that is happening. It has been happening for 13.8 billion years. It is happening now. The distances between the clusters are a little larger than they were a moment ago. The light from the most distant galaxies is a little redder. The sky is a little emptier at the farthest edges. None of this is visible from the ground. The stars look the same tonight as they did last year. The constellations hold their shapes. The Milky Way stretches across the sky the same way it always has. The local universe is stable and quiet. The expansion happens in between, in the spaces that are already large, in the distances that are already too great to cross. It adds to what is already far. It makes the empty places emptier. It is the simplest kind of change, a growing of distances, applied everywhere, all at once, without preference or direction. The galaxies are moving away. The space between them is growing, the rate at which it grows is increasing, and the universe carries on in every direction, at every scale, with no center and no edge, doing what it has always done since the beginning.